it's Zach, and today we're talking about resistors. If you watch to the end of the video, I'll share the details to an exciting new competition. So enjoy, and don't forget to like, subscribe, and click on the notification button for more electronics videos. What is the basic definition of a resistor? A resistor is a passive electronics component that is designed to resist the flow of electric current. Before explaining how resistors work, let's briefly discuss their symbology on a schematic. In Europe, the resistor symbol looks like a box with two lines sticking out of it, while in the United States, the resistor symbol is a zigzag with two lines sticking out of it as well. As an American, I think the United States resistor symbol is the coolest, but leave a comment below about which resistor symbol you like better. Resistance is measured in ohms, and the more ohms a resistor has, the more resistance it has. Circuits can also use multiple resistors to increase or decrease the overall resistance based on their configuration. The two main resistor configurations are series and parallel. Resistors in series are additive, but perhaps this can be better explained by an example. A circuit has three resistors in series. R1 is equal to 50 ohms, R2 is equal to 100 ohms, and R3 is equal to 200 ohms. Based on the fact that resistors in series are additive, the total resistance of a circuit is equal to R1 plus R2 plus R3, which is equal to 350 ohms. The total resistance of resistors in parallel can be found by 1 over R1 plus 1 over R2 plus 1 over R3 is equal to 1 over R total. Then solve for R total. Let's do a quick example. Take a circuit where R1 is equal to 500 ohms, R2 is equal to 300 ohms, and R3 is equal to 200 ohms. Find the total resistance of the circuit. By plugging these values into the equation, you get a 1 over RT value of approximately 0.0103. To find RT, take 1 and divide it by the 1 over RT value calculated previously. This gives you a total resistance value of approximately 97 ohms. What you should notice is that by putting resistors in parallel, you reduce the overall resistance of the circuit. Now that we have discussed resistor configurations, let's talk about how current and voltage interact with those. When current splits into two parallel resistors, the current divider rule allows the engineer to find out how much current flows into each parallel resistor. Let's look at the diagram. I1 is equal to I total times R2 divided by R1 plus R2, and I2 is equal to I total times R1 divided by R1 plus R2. There's a current of 5 milliamps being split by two resistors in parallel. R1 is equal to 400 ohms and R2 is equal to 600 ohms. I1 is equal to 5 milliamps times 600 ohms divided by 400 ohms plus 600 ohms, which is equal to 3 milliamps. I2 is equal to 5 milliamps times 400 ohms divided by 400 ohms plus 600 ohms, which is equal to 2 milliamps. Also, if you find out one of the currents using current divider, you can solve for the other one by subtracting the solved current from the total current. In this example, you can solve for I2 by subtracting I1 from I total. So I2 is equal to 5 milliamps minus 3 milliamps, which is equal to 2 milliamps. This is the same value we obtained from solving the current divider. When current goes through resistors in series, it's a bit more simple than if it goes through resistors in parallel. Basically, the current entering the resistors in series will equal the current leaving them. The voltage input at the parallel resistors will equal each other, and the voltage output at the parallel resistors will also equal each other. This is due to the current divider rule. The current divider rule works in such a way that I1 times R1 will always equal I2 times R2. Per Ohm's law that states V equals IR, or voltage equals current times resistance, and current divider rule, the voltage over R1 will always equal the voltage over R2. The output voltage is equal to the input voltage minus the voltage over the parallel resistor. Since the input voltage is equal for all resistors in parallel, and the voltage over each parallel resistor is also equal, the output voltage at each parallel resistor equals each other. The voltage over each resistor in series can be found by the voltage divider rule. This rule states that if you have an input voltage and two resistors in series, V1 is equal to V input times R1 divided by R1 plus R2, and V2 is equal to V input times R2 divided by R1 plus R2. Let's do a quick example. There is an input voltage of 12 volts and two resistors in series. R1 is equal to 700 ohms and R2 is equal to 500 ohms. Find the voltage over R1 and R2. V1 is equal to 12 volts times 700 ohms divided by 1200 ohms, which is equal to 7 volts, and V2 is equal to 12 volts times 500 ohms divided by 1200 ohms, which is equal to 5 volts. In order to use a resistor, you need to know how many ohms of resistance it's rated for. You could follow a time-consuming approach and measure the resistance value of each resistor you plan on using via a multimeter, or you can quickly read the bands on the resistor. These upcoming slides will teach you how to identify the resistor value just by looking at it. Each band has a color, and each color has a numerical value associated with it. Here's how it works. Black equals 0, brown equals 1, red equals 2, orange equals 3, yellow equals 4, green equals 5, blue equals 6, violet equals 7, gray equals 8, and white equals 9. This can be difficult to remember, so there is an acronym that I think you will find useful. It goes as follows. Better be right, or your great big vacation goes wrong. If you can remember this, you have taken a large step towards reading resistor values. Also, if you watch to the end of the video, I'll share the details of the competition. The location of a band is also important when identifying a resistor value. There are three main resistor labeling schemes: 4-band, 5-band, and military spec. In a 4-band labeling scheme, the first band represents the first digit, the second band represents the second digit, the third band represents the multiplier as an exponent of 10, and the fourth band is the tolerance. This can best be explained by an example. Take a resistor whose first band is brown, whose second band is black, whose third band is red, and whose fourth band is gold. From this, we know that the first two digits are 1 and 0. Then we take those digits and multiply them by 10 to the second, as the third band is red, to get a resistor value of 1000 ohms. The fourth gold band indicates a tolerance of 5%. Gold band, tolerance, what do they mean? Tolerance of a resistor is the maximum difference between its actual value and its specified value. For example, the 1000 ohm resistor we talked about previously has a gold band. A gold band represents a tolerance of 5%. That means that the resistor has a value between 1000 ohms minus 5% of its total value and 1000 ohms plus 5% of its total value. After calculating this, the 1000 ohm resistor actually has a value between 950 ohms and 1050 ohms. If you have an application that requires a precise resistance, ensure that you have a low tolerance. Common tolerance bands are as follows. Gold, as we discussed previously, has a tolerance of 5%. Silver has a tolerance of 10%, and no band has a tolerance of 20%. For more rare, high-precision applications, higher precision resistors can be used. The bands denoting these are as follows. Red equals 2%, brown equals 1%, green equals 0.5%, blue equals 0.25%, and violet equals 0.1%. Now onto the 5-band labeling scheme for a resistor. It's very similar to the 4-band labeling scheme, except for the fact that it has an additional band representing a third digit. The military spec resistor labeling scheme is identical to the 4-band labeling scheme, except that it has a 5th band that identifies the reliability level. This band tells you the component failure rate over 1,000 hours. Brown equals a fail rate of 1%, red equals a fail rate of 0.1%, orange equals a fail rate of 0.01%, and yellow equals a fail rate of 0.001%. Before moving on to basic resistor applications, let's briefly talk about a resistor's power rating. Power is the rate of transfer of energy and is measured in watts. However, in terms of calculating the power a resistor will experience in a circuit, think of power as the current squared times the resistance value of the resistor. If the power rating of a resistor is lower than the power that the resistor experiences in the circuit, the resistor will be damaged or destroyed. Common general-purpose resistor power ratings include 1/8 watt, 1/4 watt, 1/2 watt, and 1 watt. But resistors can have ratings that exceed several hundred watts if the application requires it. In this circuit, a light-emitting diode, also known as an LED, is connected to a voltage source. The LED produces virtually no resistance and can only handle approximately 30 milliamps. As the circuit has virtually no resistance to reduce the current will exceed what the LED can handle, causing it to blow. To prevent this from happening, a resistor is placed in the circuit to reduce the current. Now the LED can be used in the circuit without breaking. By adjusting the amount of current that flows through the circuit, you can increase or decrease the brightness of the lights. By increasing the resistance in the circuit, the amount of current flowing through it decreases, causing the light to dim. By decreasing the resistance in the circuit, the amount of current flowing through it increases, causing the light to brighten. Resistors, in the form of a voltage divider, can increase or decrease the volume of a speaker. By increasing the resistance of resistor AB and decreasing the resistance of resistor BC, you will reduce the volume of a speaker because a low voltage will be fed into it per the voltage divider rule. This is often achieved by using a potentiometer that will be discussed in an upcoming video. By doing the reverse and decreasing the resistance of resistor AB and increasing the resistance of resistor BC, you will increase the volume of a speaker because a high voltage will be fed into it. On to the fact I am holding a competition to discover the most creative color band resistor acronym. Send your best idea to electronicswithzach@gmail.com. The winner will get a handy data sheet covering resistor types. Hey everyone, I hope you enjoyed this video. Don't forget to like, subscribe, and click on the notification button for more electronics videos.